same thing, but we're going to do it for a different function. So we got our notes out, ready to go. Let's get some cobwebs out of those heads and get started. I'm hopeful that I don't make too many mistakes today. I'm a little bit distracted. My parents, today the movers are coming. They're moving out of my childhood home. Kind of a hard thing. We were there all, helping yesterday, but kind of a sad day. So I'm trying not to worry about it. All right, so here we go. This is our picture, and we're going to answer all these questions about it. I think having a picture helps. So I am going to try to do a quick little sketch with your help. Okay, so let's do a quick little sketch here. What can you tell me, as I try to sketch some points here, what can you tell me about, like if I'm just going to build a T-chart, what can you tell me about the X's that I am allowed to use in this picture? Am I allowed to pick any X I want? In other words, is the domain all real numbers? No. What are the restrictions on X here?
It can't be lower than negative 4.
It can't be less than negative 4. So in other words, it must be greater than or equal to negative 4. So I might as well answer my domain question right now. If I have to be greater than or equal to negative 4, and does that make sense to everybody? What happens if I'm not bigger than negative 4? It's imaginary, and I don't want to ever be that in function land. So we're going to stay real here. And my domain then is everything from negative 4 to infinity. Would you all agree with that? So in terms of the picture, I can have points back to here, but nothing over here. So this is going to be empty space, right? Okay. What happens if I put in negative 4, by the way? If I go ahead and put negative 4 in, I get
0.
What happens if I put in 0? I'm not going to put in every single number, but what if I put in 0, I get 2. Let's see, what happens if I put in 5?
3.
I'm kind of choosing my numbers wisely. Now that is not a line. That is a piece of a parabola, a sideways parabola. And before anybody says anything, we're going to spend more time with this kind of a picture. Trust me, before you say anything, look at the original equation. What would happen if I squared both sides?
Y squared.
I'd have y squared equals x plus 4. And you know enough about things squared to know they're parabolas. When you have an equation with something squared as the highest power, it's going to be a parabola. Well, x squareds are this kind of parabola. Y squareds are this kind of parabola. So when you square root that and take only the positive root, it's only the top half of the parabola. Okay. All right, so now maybe that will help me answer the rest of these questions. Does it have any asymptotes?
Maybe x equals negative 4.
Now, x equals negative 4. Okay, so I'm going to go ahead and don't draw this in. I'm going to go ahead and draw it. What's our kind of working definition of an asymptote? It's a line that the curve, it can't be, x cannot be. And we approach it, but we don't intersect it. That's not an asymptote, right? It's the lower limit of my domain for sure, but it's not an asymptote. An asymptote has to have something like this happening, or this happening. That would be an asymptotic relationship. Not everything has an asymptote. This doesn't have any. There's no asymptotes. This is getting higher and higher and higher as it goes out, so there's no upper, there's no horizontal asymptote up there. There are just none. There aren't any asymptotes. How about range? Now remember, domain was our x's, Lynn?
0 to infinity.
Exactly. And we're gonna include 0 because we have a point at 0, right? So that is very, very good. End behavior, refresh your memories. Our notation for end behavior is this, it's two parts, and this. So in other words, end behavior means what happens to my y's, what happens to my function values as x gets bigger and bigger and bigger in the positive direction. Well, tell me, what's happening to y the farther out I go?
It's getting higher.
It's high.
It's getting higher. There's no top to it. It's not like it's approaching an asymptote. It's just shooting off bigger and bigger and bigger. Now, what does this one say? What happens as I go farther? Wait a minute. Can I go farther and farther that way? Can't. This says as we approach negative infinity, this picture does not approach negative infinity, right? It's done at -4. Good. Continuity, continuous. Can I sketch this thing? It is continuous on its entire domain. So it is continuous on the interval from -4 to infinity. That's the only part we can talk about because that's the only part of this picture that we have. So it's continuous on its entire domain. Increasing or decreasing? On its entire domain, right? Extrema. Now remember, extrema technically right there because it is, that would be a relative minimum because compared to the points on either side of it, it's lower. This one you actually can talk about a relative and an absolute minimum where? At -4. And that's an ordered pair. That's a point right there, not an interval. This is not a minimum in the same sense that this would be, but it is the low point on the graph. So we can talk about it as being an absolute minimum and a relative minimum. Okay, well that was awesome. Now, I need you to get out your BFF sheet. And some of these you're going to be very, very familiar with, and some of them might be kind of brand new to you. These are 12 functions. 12 functions. If you guys have notes books and everything, you should have this, because I handed them all out for same. All right, these are 12 functions that you need at the very minimum to have memorized the name, the shape, and the equation for them. Because at some point, I will say, okay, what's the first one here? The identity function. I'll say, okay, what is the domain of the identity function? What is the symmetry of the squaring function? What is the horizontal asymptote of the cubing function? If you have the name, the shape, and the equation down, then you can probably answer all the rest of the questions the same way we did this one here a minute ago. But if I say squaring function and you don't know what I'm talking about, then you're not going to be able to do it. So today we're going to go through the pictures and the equations, and then you're going to start memorizing all this. The names are on the sheet. All right, so the first one is the identity function. Any guess as to what the equation is? I think I talked about this the other day. The identity is y equals x. That's the identity. And what's it look like? Yep, it's that perfect diagonal through the origin. This is the point 1, 1, 2, 2, 3, 3, perfect diagonal through the origin. That's the identity. We are not going to, you and I, fill in all that information after we get all the pictures up. We'll go back and pick out a couple to fill in all that. But we're not going to do them all. Okay, squaring function, y equals x squared. What's the shape of that guy? You know this, y equals x squared. That's your parabola. Right? Y equals x squared. Cubing function, y equals x cubed. Anybody know what that one looks like? Yep, that's exactly right, Sarah. It's this guy. By the way, who knows another thing that has that kind of shape? It's not exactly the same, but it has a similar shape. That's your tangent curve. When you graph, sine, cosine, and tangent, when you graph tangent, that's the shape. But for us, it's the cubing. It's the cubing function. All right? Reciprocal function. We got these. Reciprocal function. Equation is y equals 1 over x. That's a reciprocal, right? What's the reciprocal of 5? 1 over 5. So the reciprocal function is y equals 1 over x. This one is a little bit wacky. This one, because x cannot be 0, has a vertical asymptote at 0. Y will never be 0 either, so it has think about that fraction, that will never equal 0. It has a horizontal asymptote at 0. If x is positive, y is positive. And if x is negative, y is negative. That is a picture of your reciprocal function. So that one, there's a lot of interesting things to talk about with that guy. But that's your picture for the reciprocal function. Square root function is the one we just graphed. The square root function, now the one we just graphed had an additional number and stuff under here, right? This one is just a 0, so it has this shape right here. That's your reciprocal, or your square root function. No asymptotes in that picture at all. And then your exponential function. Now, want to clarify this. When we are just memorizing an equation, we'll say e to the x. That's Euler's constant, 2.718. Base of the natural logarithms. I'm ringing some bells there. That's what that e is. But the general shape we're going to talk about is going to be the shape for anything to the x power. So 2 to the x, 5 to the x, they're all gonna have this shape. All right, so what is that shape? Well, if you think about it for a second, what happens if x is 0?
It's 1.
That's just 1, because anything to the 0 power is 1. So I know it's gonna have this point, so I'm gonna label that point. And that will be true no matter what this is, right? I can make that a 2, it's still going to be 0. Or 1, I mean, if I put in 0. All right. Think about, this number is approximately 2.718. If I raise that to a power, will it ever be negative? Can you raise a positive number to a power and make it negative? No. So this one's gonna have an asymptote at y equals 0, because this curve is never going to go negative. And if you think about it, the bigger x gets, raise 2.718 to bigger and bigger powers, isn't it just gonna keep getting bigger? So this is kind of shoot up like this. It's called exponential growth, when it just explodes. But on this end, do you remember what happens when you raise numbers to negative powers? You put it under 1, so they actually become smaller and smaller. So this is what it looks like. That is your exponential. So when you hear people talk about exponential growth, that means it's getting really, really big, really, really fast. Okay, so far so good, we're half done. Now, they call it in your textbook the natural logarithmic function, so it's ln x, but this is going to be the shape for any logarithmic function, so log, log base 2, whatever you want, the general shape is going to be the same. Anybody know anything about taking the logarithm of numbers? Can you take the logarithm of any number you want? Pull your calculator out. Take the logarithm of 0. Just hit log 0 or ln 0. What happens? Yeah, you can't. Doesn't it give you an error message? Try log -2 or ln -2. I can't do that either. When you take the logarithm of something, that something must be bigger than 0. So I have a vertical asymptote at x equals 0. This one and that one are inverses of each other. And we haven't spent much time or any time, you and I, talking about what that means. But if you are inverses, you undo each other. So if I put 0 in and get 1, over here, if I put in 1, I get 0. So that point is always going to be on your logarithmic curve, just like this point is always going to be on your exponential, unless you've done something to modify it. This is your logarithmic curve. So notice that the exponential had an asymptote at y equals 0, but the logarithm has an asymptote at x equals 0, like opposites of each other. They both shoot off into space. This one, of course, not going nearly as fast, but this is going up, 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 up as it heads off the page. That is a picture of all of your logarithms. ln in particular, but all of your logarithms have that shape. Now we've got our trig curves. The only two that are part of the BFFs are the sine and cosine. So our abbreviations, SIN, that's sine. The name is SINE, but we abbreviated SIN. In math class, don't say sin, that's religion. That will just make you sound goofy. This is sine, okay, sine. And then cosine, COS. These two curves, we're gonna spend a lot of time with these two, a lot. But for just getting started, I want you to label your y-axis with 1 and -1. And I know the grids are really tiny, so you don't have to do just one. You can like go up 4 or 5 blocks and call that 1. So it's not so squished up, because the whole curve is gonna happen in between 1 and -1. Now, for the sine curve, once you put a dot at the origin, and I want you to draw a little hill going up to 1 and back down, as nice and symmetric as you can. And then I want you to draw a valley, same thing. In both directions. Put little arrows on the end because the sine curve keeps going and going and going. Now we're going to talk about domain for this a little bit later on. But right now, get the shape down. That's your sine curve.
What's the value of the x-intercept?
Okay, we're going to talk about that.
Okay.
Technically, see, it's a little sketchy because, okay, this is pi radians or 180 degrees. But I don't want to get all hung up in that right now. I want you to know the shape of the sine curve. We're going to spend a lot of time graphing all kinds of sines later on.
Would there be any asymptotes for this?
No. The curve doesn't approach, but not intersect anything. It just keeps waving around, back and forth, back and forth. No asymptotes. Now, upper bound, lower bound, absolutely, but no asymptotes.
Does it go all the way to 1, or does it just like
It goes
get
up to
right
1.
near?
No, it's 1.
That's 1.
This value
Something
is
1.
pi over 2 comma 1. That's where it is, pi over 2 radians comma 1, yep. And then this one is negative pi over 2 comma -1, yep. All right, so this is the shape. We're not worried so much about the x labels yet. I'm gonna come back and give you the domain and range, just, well, you know the range, just so you've got it. But let's just hold off on getting specific about the x values. All right, now the cosine has exactly the same shape, except it's positioned differently. So you need to sketch in your cosine carefully, but they are exactly the same shape. Think about that for a second. Would you agree that they have exactly the same shape, exactly the same characteristics? What's different is the sine actually goes through the origin, but the cosine doesn't. Its y-intercept is up here at 1. As goofy as it sounds, as a good Catholic girl, original sin. Sine goes through the origin. That's how I remember it. Now, there are mathematical reasons for it going through the origin, but in terms of just a quick sketch, which of these is a sine curve? This one is, because it goes through the origin. All right, 3 more to go. What have we got? Absolute value, greatest integer, and logistic. So your equation for the absolute value is, of course, absolute value x. This one you did a lot with last year. Do you remember the shape of this one?
A V.
It's a V from the origin, right? Now, this is the basic shape. You can put numbers up here and move that V around, but this is the basic shape. It has all the same characteristics as which other one of our BFFs. Everything's the same.
Identity?
The squaring.
The squaring, the x squared. Isn't that very similar to x squared? I mean, x squared has a curve, a UE shape instead of a V, but in terms of domain, range, increasing, decreasing, all that, they're exactly the same. Greatest integer is my personal least favorite. I don't like to use the word hate it, I just hate it. You can denote it a couple of different ways. Sometimes you see it like this. Sometimes you see it like this. Just int x. Sometimes you see it with extra little set of bars in here. Something like that. One of those is the notation you're going to use for greatest integer. And the greatest integer function is one that you might have thought of as a step function. So, and I know your grids are really tiny, and I apologize for that, so scale it however you want. But we want to put a solid dot at 0, at the origin, and then a bar over to whatever you want to call 1, however far you want to go, call that 1. And then step up 1, put a solid dot, and another bar over to 2. And then step up 1 again. So these little bars are 1 unit long, and the steps are 1 unit high. So 1 unit this way, 1 unit this way. And of course, it goes backwards too. Now, the greatest integer function looks like this because, I think you may have talked about these last year. The greatest integer function says that y is the integer closest to x, but not bigger than x. So, if we had the greatest integer of 3, that would be 3. But if we had the greatest integer of 3.1, that would also be 3. Because the value is the integer closest to this number, but not bigger than it. So the integer closest to 3.1 is 3. So if you look at my picture, that makes sense because any x value between 3 and 4 is going to be plotted with a y value of 3. 3.1 goes to 3, 3.2 goes to 3, 3.3 goes to 3. So all of these have a greatest integer value of 3, every number between 3 and 4. But once you get to 4, then you skip up now you've become 4. And then everything between 4 and 5 plots to 4 and so on. Real life applications of these all over the place. I don't know why I don't like them so much because they're all over the world. Think about when you mail a letter. You buy a first class postage, you put it on there. But if your letter weighs more than whatever their weight limit is, you have to put on additional postage, right? So let's say anything between 1 ounce and 2 ounces, you gotta put on an extra stamp. Anything between 2 and 3, you gotta put on another stamp. We don't use half stamps, right? Same thing in a parking garage. Don't you pay the same? Well, depending on what garage you're in, but you pay so much for the first hour, and then you pay an additional amount for the second hour, third hour, and fourth. They don't do like, oh, I was here for 1 hour and 1 minute. No, you were here for more than 1 hour, so you pay 2 hours worth of parking. All right, and then the last one, the logistic function, might be the one you are least familiar with. There's your equation for the logistic function. We're going to look at a lot of modifications of this one, but that's the general shape of the equation. And this is the general shape of the curve. Put an asymptote, horizontal, asymptote at y equals 0. Put another horizontal asymptote at y equals 1. So again, obviously I'm scaling this differently so it's not all squished up on that tiny little graph. This is 1. And that's your curve. This point is not anything, I mean, this point varies from problem to problem, so don't worry about, for this equation, it would be 1/2, but it's not always, so I don't want you to get in that group. And that's your logistic function. The logistic function we use most frequently in modeling population. Think about it for a second. Think about a population, even in Fort Bend with the deer. Periodically, what do they have to do to the deer population? Some of you are going to be offended at this, but what do they do sometimes to the deer population? They open up hunting, right? Why do they do that? Because there is a limit, an upper limit to any population. After, I mean, if you get too many things trying to live in the same space, they can't survive because there's not enough food or space or whatever, right? So populations are often modeled logistically. Okay? All right. So now I'm going to let you pick whatever function you want. Let's run through the whole list for that function. So pick one and we'll go through it with all of our vocabulary. It's called function analysis. We're going to analyze the function using the criteria on the sheet. So which one do you want to do? Greatest. Okay, I say this is the one I hate and this is the one we have to do. Yeah. Okay, so remember these bars are 1 unit long and 1 unit spaced apart that way. So, okay, so here we go, domain. And range. Continuity. All right, so here we go. What do you think, guys? Some of these aren't going to have nice, neat little answers, but you asked for it, so here we go. Domain is all real numbers. Very, very good. So somebody up here is saying that X can be absolutely anything, and it can. It can. X can be anything. What about the range, though?
You don't want to be one number. Whatever, like.
Only whole numbers.
Close, not whole numbers. Let's refine our vocabulary. Integers, yeah. So the range is the set of integers, and the set of integers, can't really do it with an interval, is this set of numbers. Would you agree with me? Every y value in that picture is one of these numbers. Every y value. So all of these y's are 0, all of these y's are 1, all of these y's are -2. This is your range. Beautiful. All right, what about continuity?
It's not.
Oh, it's jump.
It's a jump discontinuity. Love it. Love that vocabulary. Trying to get all my stuff written down here that we need. All right, so this is not continuous. So I'm going to say not continuous. And then in parentheses, I'm going to say jump discontinuity, because that's exactly why it's not continuous. Very good that you remembered that. Super. All right, increasing or decreasing. See, this is where things get messy. See this little piece right here, is that increasing
No.
or decreasing?
It's constant.
No. Is this increasing or decreasing? No. Now, when you look at the picture, the steps are going up, right? The steps are going up. How are we gonna describe this? It's a messy one, I don't know. How do you wanna describe that?
It goes up. Because on like the y-axis, right? Like they're going up. Like those little dashes that go to the side, they're getting higher.
Each step is getting bigger.
Well, like it's
Right.
going sideways. But they're also getting smaller. Yeah.
No, whenever we're having a conversation about increasing or decreasing, it's left to right. Only look left to right. So this is increasing, but, okay, so what is it increasing on?
The y.
Y grows as X grows, or
That's not true.
The x-axis.
Is X is growing right here, is Y growing? No.
So then isn't y sideways?
Huh?
Is y sideways? Isn't it the sideways one? X is up and down.
Here the X's are getting bigger. Look, Sabrina, the
Yeah.
X's are getting bigger, but the Y's are staying the same on this little piece.
So
Now,
the
when I
y
get
is the
to
vertical
here-
one?
Y goes up and down, yes.
Wow, okay.
Yeah.
Sabrina, I meant X all along.
So, what are we gonna say? We're gonna say
H on y-axis.
increasing, but not on the entire domain. Is that fair?
Is there a way to say it's only increasing on specific parts of the domain?
Well, how are you gonna describe specific parts of the domain? It's only increasing, I guess, at the integer values of X.
Yeah.
So yeah, if you wanted to say that, you could. Increasing at integer values of X. So we can say that. Increasing at integer values of X. You guys picked this problem, not me, okay? It's increasing at integer values of X. So at this value right here, it increases. I gotta be careful though, because it doesn't really, I guess it doesn't. Yeah. Okay. Symmetry. No. It almost looks like it could have symmetry, but these bars would have to be turned around, so none, no symmetry. Found it above or below?
No.
I've been using the word relative. They're using local on this sheet, same idea. Extreme. Vertical asymptote. Horizontal asymptote on there? Yeah, I have to write it down. Vertical asymptotes, there aren't any. Horizontal asymptotes, there aren't any. And then end behavior. End behavior is
As
what happens as you go off the page. We write it that way. What happens as we go off the page?
plus infinity.
This way, aren't we going up, 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 up,
Yeah.
up? So that would be positive infinity. And what's happening this way? Down, 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 down. So that was a disaster. We got it. Okay, let's do one more. Pick another one. Let's do one more.
Well, I guess it's,
Yep.
I guess I don't think so, Sunday afternoon, it's like Saturday afternoon, it's like. I need to sleep, it's like why you're in football. I'll leave after the first one.
Okay. So the reciprocal function, is the one that has an asymptote at x equals 0. And y. All right, what's our domain?
Negative infinity to 0, and then bound 0 to infinity.
Everything except 0, right?
Yeah.
So we're gonna go from negative infinity to 0 and 0 to infinity. Your domain is everything except 0. X cannot be 0. Remember, the equation is this, so it makes sense. X can't be 0. Okay, what about our range? Same thing, very good. Y can't be 0 either. Look, you got an asymptote running right through there. Y can't be 0 either. Super. Continuous?
No.
What happened?
Infinity.
We have an infinite or non-removable discontinuity at x equals 0. So, let's say infinite or non-removable discontinuity at x equals 0. So we can draw this piece just fine, and we can draw this piece just fine, but we have that break right there.
Wouldn't it also be at y equals 0?
Remember, the discontinuity, okay, we're looking as I draw the picture from left to right. Okay, so what makes me lift my pencil? Isn't this what makes me lift my pencil? This isn't causing me to lift my pencil. It's bounding me, but it isn't making me stop the picture. It's not breaking the picture as I draw it left to right. Now, be careful, because someone might say that this is continuous on its domain. Now think about that for a minute. Is that a true statement? It's continuous on its domain.
It doesn't include 0.
The domain doesn't include 0.
Yes.
So if you take away that exception, that 0, take that out of the picture, is that continuous?
Yeah.
On its domain, it is. It's a discontinuous picture. I don't want you to get the idea that this is continuous. But if this is described as the only possible x's, then you are continuous on these two pieces, right? Individually. All right, increasing or decreasing?
Decreasing on both.
Remember, left to right, left to right. Which way's my pencil going?
Down. Down.
This is decreasing. From negative infinity to 0 and from 0 to infinity. That thing is decreasing the whole time.
We just say decreasing on its domain.
Yep. Symmetry. Now look at it. Does it have any kind of symmetry?
Yes.
To what?
Y equals negative x.
Okay, here's the line y equals negative x. We've not talked about that one. But does it have symmetry to that line?
Yes.
All right, so let's add negative x. Anything else kind of obvious that it might have symmetry to? What about the line y equals x?
Yes.
Does it have symmetry about that one too? What about either axis? Does it have symmetry to the x-axis or to the y-axis?
No.
No. What about to the origin? Does it have symmetry about the origin?
Yeah.
Yes. Because it has symmetry about the origin, we could call this an odd function. Remember we talked about that the other day, that if it has symmetry about the origin, it's odd. So the reciprocal function is an example of an odd function.
Wouldn't having symmetry over the origin be the same thing as symmetry of y equals x?
Y equals negative x.
No, just y equals x.
Y equals x. No, because the test for symmetry for y equals x is you switch the variables. So in this case, yes, because this is actually symmetric to both, but you can be symmetric to the origin and not be symmetric to the line y equals x. Let me see if I think of one right off the top of my head. Okay, so this one would have symmetry about, so this is the line y equals 1/2 x, okay? It has symmetry about the origin, because if I change both signs, it's really the same equation, right? But if I switch the x and the y, I don't get the same equation. So this one, so consider this line right here. It has symmetry about the origin, but its reflection across the identity would be this line right here. So it does not have symmetry about the line y equals x. Okay, if you just remember your tests of symmetry, then you can check everything. Okay. All right. Quickly, we gotta get through the rest of this. We did symmetry bounded. Is this thing bounded? Be careful. Is it bounded above?
No.
No, because what happens? It shoots all the way up, right? Is it bounded below?
No.
No, because it shoots all the way down. Think of your sine and cosine, guys. They are bounded. They go forever, but they never go above 1 or below -1. Local and absolute extrema.
None.
Asymptotes, yep, we got them all. We've got vertical at x equals 0 and horizontal at y equals 0. End behavior. This is our notation. This is what we write, our notation. Going that way, what's our end behavior? What's curve doing? Well, so it's getting closer to 0 from the top. And then as we go that way, we're still getting closer to 0, but it's from the bottom. All right, if we have time someday, we'll come back and do a couple more. That was kind of fun. But right now, we got a couple of sketches we need to get done. We only have 6 minutes. So keep your BFF sheet out unless you already know your shapes. Because what we're going to do now is talk about how we can manipulate our shapes by doing things to their equations. Like in this case, sticking a +1 in there. Versus sticking a +1 in there and sticking a 2 and a 1 into the problem. Okay? So who remembers, first of all, what shape are these? These are V's. What does this do to the V? One to the left. Lewis is exactly right. This takes me 1 unit to the left. So I have my exact same V, but it has moved 1 unit to the left. What about this one? What has this one done? 1 up. So these two are exactly the same size, shape, everything. They have been positioned differently, 1 unit up. Now, this is not a V. What shape is this? But it's the same idea, but we've done both. So what does this do? Right 2 and up 1. So now I have my parabola, right 2 and up 1. These are called translations. When you pick your curve up and put it down somewhere else, you're translating it. Okay. Everybody good? Inside the parentheses or the bracket, whatever you've got, moves you left and right. Outside moves you up and down. All right, let's look at these next ones because they involve negatives now. So another kind of transformation is a reflection. And a reflection is what happens when you stick negatives into your problem. Both of these negatives, and in fact the other one too, are in exactly the same spot. They're out in front of the equation. Does anybody remember what happens when you put a negative on your function out in front like that? Mr. Fahey, was your hand going up?
Yeah, doesn't it flip it?
Flip it how? Yes, reflections always flip one way or another. What, or negatives always flip. What's this one doing?
Isn't it like it flips across the y-axis? Like
Unfortunately, no. This one's upside down. This flips you upside down. This one, if you think about it like this, Liam, is this the same equation? Could I rewrite my equation like this? So that negative is changing the sign on y. So it's turning me upside down. So think about what a normal cube looks like. Isn't this the negative of it?
Yep.
So instead of increasing, it's decreasing because you turned it upside down. All right, so what's that one gonna look like? This would be the normal. Watch my hand, that's the normal. So won't this be the negative? Now this one's crazy, because two things have happened. So I'm gonna go ahead and sketch. This is my exponential. So I'm gonna go ahead and sketch. This is the regular curve. You have an asymptote at 0. What has happened to this picture now? Instead of shooting up like this, isn't it going to be down here like this?
Yep.
And furthermore, every point is getting shifted 1 unit to the left. So if I turned it upside down, that point would be 0, -1. But it's going 1 unit to the left, so that point is now at -1, -1. And it looks like that. All right, good work. We'll pick this conversation up tomorrow. 1.2 homework, you already talked about that, right? Due on Thursday. You're welcome, have a wonderful day. Memorize those BFFs, guys. Get them learned. We'll be having a quiz at some point.